It is very useful to know whether a matrix is invertible or not. Say you have a system of equations Ax equals b, and when matrix A is invertible, you know that the system has exactly one solution. One way to determine whether a square matrix is invertible or not is by computing its determinant. In this video, I will show you how to do this. We start with a 2 by 2 matrix. Remember that a matrix is only invertible if you can row reduce it to the identity matrix. That is only possible if quantity AD minus BC is non-zero. The inverse matrix then features that same quantity. If AD minus BC is equal to 0, matrix A is singular. This scalar quantity AD minus BC is called the determinant of matrix A. You can write it as DET of A or as A between vertical bars. Also, for larger square matrices, it holds that A is invertible if and only if its determinant is non-zero. For example, this matrix has a determinant of 2 times 7 minus 3 times 4, which equals 26. So this matrix is invertible. Now a 3 by 3 matrix. If you want to find the inverse matrix, again you have to reduce A to the identity matrix. That is only possible when a certain scalar combination of the elements of A is not equal to 0. We call this quantity again the determinant. The determinant of a 2 by 2 matrix is easy to remember. The determinant of a 3 by 3 matrix has 6 terms. The determinant of a 4 by 4 matrix has 4 factorial terms, so you cannot memorize that. For the larger matrices, I will show you a recursive procedure, the cofactor expansion. To define a cofactor, we need 2 more concepts. The first is submatrix. This 4 by 4 matrix has 16 elements, usually denoted by A sub ij, where I denotes its row in matrix A and j its column. The matrix has 16 submatrices, one for each of the elements of A. Each submatrix is formed by deleting one row and one column of matrix A. For example, submatrix A32 is matrix A, but without its third row and without its second column. So this submatrix is a 3 by 3 matrix. We also need the checkerboard pattern. That is defined as the matrix with elements -1 to the power I plus j. That gives this pattern. Easy to remember. Just start with a plus for the top left element and alternate. Now we can define the cofactors. Each element of a square matrix has a cofactor Cij. Cij is defined as the checkerboard sign times the determinant of submatrix Aij. So a cofactor is a number. For example, for this matrix A, the cofactor of the element in the first row and the third column is -1 to the power 1 plus 3 times the determinant of submatrix A13. So that makes +1 times the determinant of this 2 by 2 matrix. This 2 by 2 determinant equals 3 times 4 minus 1 times 2. So the cofactor is 10. Now that you know what a cofactor is, we can start calculating determinants. This is the formula for the cofactor expansion for a determinant. Multiply each element of the first row by its own cofactor and add these products. Or, said differently, the determinant is the sum over the first row of A of the products of 3 factors: the checkerboard sign, the element of A, and the determinant of its submatrix. If A is n by n, its submatrices are n-1 by n-1. So a cofactor expansion expands a determinant into determinants that are one size smaller. You do that repeatedly until you have reached 2 by 2 determinants. And for those, you have a formula. Here's an example. The 3 by 3 determinant is expanded into 3 terms. Each term has a sign according to the checkerboard pattern. Each term has an element of the first row of A. And each term has a determinant of a submatrix. The first determinant is of submatrix A11. The second of submatrix A12. And this is the third one. The 3 by 3 determinant has been expanded into 2 by 2 determinants, which can be readily calculated. So the determinant of this matrix is 30. You can rearrange the terms of the cofactor expansion, and as it turns out, you can just as well expand across one of the other rows. This is the formula for the expansion across the ith row. For example, we can expand the determinant of the same matrix across the second row. Signs, elements, determinants of submatrices. And indeed, we get the same value for the determinant. Isn't that neat? Moreover, still other rearrangements of the terms give the cofactor expansion across a column. For example, across the third column. Signs times elements times subdeterminants. And again, the same number 30. For this matrix, there are 3 cofactor expansions that I haven't shown you. You may check those yourself. Now, an example of a 5 by 5 determinant. You are free to choose across which row or column you expand. Therefore, you can choose a row or column with many zeros. For example, let's start with an expansion across the third row. The cofactor expansion now has only one non-zero term. That term is the checkerboard minus sign times element 2 times the determinant of submatrix A32. Let's now expand this 4 by 4 matrix across the third column. That column has only one non-zero element as well, the one in the first row. The checkerboard sign of element 3, 1 is a plus. So plus 1 times the 1 of the element times the determinant of this 3 by 3 submatrix. Let's now expand across the third row to take advantage of the only zero left. This expansion has 2 by 2 determinants, and thus we have reduced a 5 by 5 determinant step by step into 2 by 2 determinants. The determinant of this matrix is -6. The matrix is invertible. Note that this cofactor expansion was still doable because this matrix has so many zero elements. Soon you'll learn how you can create more zeros in other determinants as well. In this course you will see a number of uses of the determinants. The first one is to check whether a matrix is invertible or not. The proof for that theorem is given in another video. In this video you have learned to calculate determinants using a cofactor expansion.